Antonio studies figure eight numbers and thinks he has found a pattern. He claims that each triangular number plus each square number results in each septagonal number. Antonio shows an example to support his claim. Write polynomials for each type of figure eight number to determine whether the pattern Antonio noticed is true for every triangular, square, and heptagonal figure eight number. Use the problem-solving process. Justify your solution and determine if your solution is reasonable. Okay, so first, understanding the problem. Antonio thinks because he has this one example where we have a triangular, we can also see here each one of these figurates has two dots on the bottom. So we'll just call this a set. We'll call it n equals 2. And so he sees that when each one has two dots at the bottom, then the triangular has three dots total, 4, and then plus 4 for the square will equal 7 for the heptagonal. And so we need to see if this is true for all examples. And so here's a diagram of then the other triangular figurates when you add a dot each time to the bottom row and keep all the triangulars proportional. We see that it grows with a whole row of dots on the side each time. And then with the heptagonal, a similar deal each time, adding another dot at the bottom and then proportionally adding more dots to keep the heptagonal proportional each side. We see that it grows with more and more dots each time. And then with the square, then same thought, and each time it's just going to grow one at the bottom and then it proportionally grows out. And so I've gone ahead and I put these numbers of the figurates into a table with n being the set number. And so if n is 0, that means that there's 0 dots. And so of course t of n, which I've called the triangle dots, s of n, the square dots, and h of n, the heptagonal dots. And so it's going to be 0 if there's no dots, 1, there's going to be 1 dot, that's kind of the starting point for all of them. And then 2 we see is his example and the total number of dots. And then 3 and 4, how each one will increase in dots. And so we need to go ahead and make a plan. So if we could find equations for t of n, s of n, and h of n, we could add up the equations and see if t of n plus s of n equals h of n. If we come up with it generically in terms of n, then we could see if it works for all numbers. And so let's go ahead and find the finite differences. So for t of n, just subtracting as we go, also notice that n increases here by 1 each time. And so we know that delta of n is going to be equal to 1, which is important. And then going on, t of n, 10 minus 6 is 4, 6 minus 3 is 3, and so on. Continuing on here, since those are not constant, 4 minus 3 is 1, 3 minus 2, etc., and those all turn out to be 1. And so then finding the actual equation, we know that this will be quadratic, and so we know 2a will be equal to the second difference, which in this case is 1. And so dividing by 2 on each side, we see that a equals 1/2. Then we know a plus b equals the first difference between 0 and 1, which in this case is 1. And so 1/2 is a. So a plus b is 1. Subtracting 1/2 on each side, we get b equals 1 minus 1/2, so b will equal 1/2. And then c will equal 0, since when n is 0, t of n is 0. So the final equation for t of n will be 1/2, since that's a, n squared, and then plus 1/2, that's b, n, and then c is 0, so that'll be it. Moving on, for s of n, we can actually see a pattern from here. Just it being a square, if you notice here, 1 is the same thing as 1 squared, 4 is 2 squared, n is 3 squared, and 16 is 4 squared. And so you could do finite differences, but we can look at that and see a pattern also. And so we know that s of n, since it's a square, will be equal to n squared, and that fits the pattern of all of those numbers there. And then h of n, let's go ahead and find the finite differences since I see no pattern immediately. So for the first differences, we do not have a constant, but then finding the second differences, we see that we do have a constant of 5. And so let's find the equation. 2a will equal 5, the second difference, so dividing by 2 on each side, then we see a equals 5/2, and then a plus b will equal 1, the first difference between 0 and 1. So then substituting in a, 5/2 plus b equals 1. Subtracting 5/2 on each side, then we get b equals 1 minus 5/2, and 1 is just 2/2, so 2/2 minus 5/2 will give us negative 3/2. And then c will be equal to 0 again, since when n is 0, h of n is 0. And so then putting that equation together, we get h of n equals a, which is 5/2, n squared, and then b, which is negative 3/2, n, and then c is just 0. So now we need to see, does t of n plus s of n equal h of n. And so adding those together, does 1/2 n squared plus 1/2 n plus n squared equal h of n? So let's just add these together. Well, 1/2 n squared plus n squared, that's 1/2 plus 1, which is the same thing as 3/2 n squared. And then we still have plus 1/2 n. And we see that that does not equal h of n, which is 5/2 n squared minus 3/2 n. And so according to our equations, those are not equal. Let's just check for reasonableness in our answer. And let's try, the example that Antonio gave was with n equals 2. Let's try n equals 3 and see if that works in our table. So does t of n plus s of n equal h of n? 6 plus 9 actually equals 15, which is not equal to 18. And so we see also in our table that there is an example where that does not work. That could be a counterexample. And so Antonio is not correct in assuming this for all numbers. Let's go ahead and summarize our answer. Understand the problem. Antonio found one case where a triangular number plus a square number equal to a heptagonal number. The problem asks if this relationship is true for every triangular, square, and heptagonal number in a sequence. Make a plan. Make tables to represent the figure number patterns and use the patterns in the tables to write polynomials to represent the figure numbers. Let n represent the position in the sequence of figure numbers. Determine if the sum of the triangular number function and the square number function is equal to the heptagonal number function. Carry out the plan. Triangular numbers 1, 3, 6, 10 can be represented by the function t of n equals 1/2 n squared plus 1/2 n. Square numbers 1, 4, 9, 16 can be represented by the function s of n equals n squared. Heptagonal numbers 1, 7, 18, 34 can be represented by the polynomial function h of n equals 5/2 n squared minus 3/2 n. If the pattern Antonio noticed is true for all triangular, square, and heptagonal numbers, then the heptagonal numbers will be represented by t plus s of n equals 3/2 n squared plus 1/2 n. Since h of n does not equal t plus s of n, the pattern Antonio noticed is not true for every triangular, square, and heptagonal figure number. Look back at your work. Finite differences can be used to determine the functions t of n, s of n, and h of n. Functions can be added together by combining like terms and applying the properties of algebra. The function t plus s of n can be compared to h of n for equivalence. Since t plus s of n and h of n are not equivalent, the pattern Antonio noticed is not true for all figure numbers. To evaluate the solution for reasonableness, select a different set of figure numbers. The third numbers in each sequence are t of 3 equals 6, s of 3 equals 9, and h of 3 equals 18. 6 plus 9 equals 15, which is not equal to 18. Therefore, for the third set of figure numbers, t of 3 plus s of 3 does not equal h of 3 and is a counterexample for Antonio's pattern.